The first two questions are from section 8.1. And really it's just, can you take an nth term, or in this case we have what's called an explicit formula, and then this case here is what's called a recursive formula. So can you take those and generate terms of a sequence? So for that first one, to find the first four terms, that's where you would plug in n equals 1, n equals 2, n equals 3, and n equals 4 into that formula right there. So for the first term, you'd have -1 to the first power, because anytime you have an n, you would plug in 1 for that first term. So a -1 to the first power, and then 1 plus 1 squared. And then for the second term, you'd do n equals 2 now, so you'd have -1 squared, and then 2 plus 1 squared. And for the third term, you see how that works?
Yeah, you just plug in the numbers, right?
Just plug in the values, yeah. And then for the fourth term, so it looks like we'd get -1 over 1 plus 1 is 2, 2 squared is 4, so -1/4 for that first term. And then for that second term, -1 squared is going to be a +1. And then 2 plus 1 is 3, 3 squared is 9. For that third term, we're going to have a -1 on top, and then 4 squared is 16. And for that fourth term, we'd have 5 squared, which is 25. So those are the first four terms. And then for the 100th term, just do the same thing, but you plug in a 100. So -1 to the 100th power is +1. And then, boy, let's see, 101 squared. Let's see. It's going to be 10,201. So that's really the main point of 8.1 homework is, can you take a formula like this and generate a certain number of terms of a sequence? But there's two different kinds of formula. This one is called an explicit formula, where all you do is plug in the n value that you want. If you want the first four terms, you plug in n equals 1 through 4. The second type of formula for here, question 2, is what's called a recursive formula. And it will always tell you at least the first term. That's what a sub 1 is right there. It tells you the first term is 5. And then this part of the recursive formula says that any term, that's what a sub n means, any term is found by taking the term in front of it. That's what a sub n minus 1 means, and then you subtract 4. So if I want the next term in the sequence, this one right here, I could say, all right, this is a sub n, that's the term I want. In order to find a sub n, I have to go to the term in front of it and subtract 4. So the term in front of this one then is 5. If I take 4 from that, I get a 1. So the next term is 1. And now I want this term, and I could say, all right, now this is the term I want, a sub n. In order to find that, I've got to go to the term in front of that one and subtract 4. So I'm always going to the term in front of it and then subtracting 4 every time. So the next term would be subtracting 4, which is -3, then subtracting 4 to get -7, then -11. So the limitation of a recursive formula is you wouldn't be able to skip to the 100th term like we did in the problem above, because in order to find the 100th term, you'd have to know the term in front of it, the 99th term, and in order to get that one, you'd have to know the term in front of that one. You following? Does that make sense?
Yeah.
So that's the limit of a recursive formula. It helps you generate terms quickly in succession, but you can't skip around. So that was really the gist of 8.1. It was a pretty easy homework, just generating terms of a sequence there.
Okay.
Question 3 is from 8.2. So is, question 4 is from 8.2, and question 5. These are all from 8.2. So 8.2 was introduced an arithmetic sequence. An arithmetic sequence is a sequence where you're always adding or subtracting the same number every time. So like this one here that we just finished, we're subtracting 4 every single time, so that's called an arithmetic sequence. So for an arithmetic sequence, we need to find the nth term, or a formula like this. This is called an nth term formula. We need to find an nth term formula where the fifth term, a sub 5, is 44, and the 17th term is 152. Let's see. Hey, we got Joseph. Hey, Joseph.
Hey.
Hey, we're just working on the practice exam.
Okay, perfect.
We're on question 3, and I'm recording it, and I'll post it since you missed question 1 and 2.
Okay.
Now, David, I think it was you. You were asking a question on the homework a couple of days ago, and I think this one is very much like the one we were working on. If the sequence is arithmetic, with arithmetic you want to kind of think linear function.
Oh, yeah.
And when you think linear function, we're thinking slope, right? Y equals mx plus b. So if an arithmetic sequence can be thought of as a linear function, the first thing we're going to want to find is the slope. And the way we did that in the homework was, it's just the difference in y values divided by the difference in x values here. If you want to think about this as an input and an output table, when n equals 5, a sub n is 44. When n equals 17, a sub n is 152. So we can find the slope just by doing what we would do in a algebra course. So 152 minus 44 is the change in y values, and then 17 minus 5 is the change in x values. Let's see, 152 minus 44 is 108. So I have said that we're finding the slope if this were indeed a linear function, but a slope corresponds with arithmetic sequences to the common difference. So the common difference d equals 9. What that means is we're just adding 9 every time to get from term to term. So from the 5th term to get to the 6th term, we would add 9. To get to the 7th term, we'd add another 9. So there's our common difference. So we know that the nth term formula is going to be a sub n equals 9n. But what we don't know is this value here. And what I'm trying to relate this to is a linear formula, linear function y equals mx plus b. But what we could do now is use one of these values, an n and an a sub n pair, like this one, 5 comma 44. I could put a 5 in for n and a 44 in for a sub n, and that'll help me find that missing value there. So 9 times 5 is 45. So that means that missing value has to be negative 1. And that would be the nth term. And I always recommend, once you have come up with what you think is an nth term formula, just test it. According to what we started with, it said that the 5th term's got to be 44. And that's still got to be true in this formula. So if I plugged in a 5 for n, for this n right here. 9 times 5 is 45. 45 subtract 1 is 44. So it's never a bad idea to check that. But that's what they were asking for when they say nth term for an arithmetic sequence. Any of you two have any questions on that one? Okay. The key word in this problem was arithmetic. That's what made it possible to use a linear function and find the slope, kind of like we did.
Wait, could you explain again? Where do you get the -1?
Yeah. So the nth term formula is going to look like this, where it's instead of y equals mx plus b, m is the same as the common difference. It's kind of like the slope, and we found that over here, right?
Oh, yeah.
And then x and n, those are just our variables. What I didn't know was that value. That's why I put a question mark right here. But I did know that when n equals 5, that a sub n equals 44, so I just plugged in this pair right here, 5 comma 44. 5 for n and a 44 for a sub n. Then the only variable that was left was this unknown value we were trying to find. And then the 9 times 5 is 45. I just subtracted the 45 over from there.
Oh, okay.
Does that answer your question?
Yeah.
Okay. All right. Question 4 is actually a lot more straightforward. Again, the key word here is that this is an arithmetic sequence. And so the nth term is going to be a sub n equals, and if we're thinking again, y equals mx plus b, because it's linear in form, then we're going to want the common difference. So we need to figure out what the common difference is from term to term, and it looks like we're subtracting 7. So the common difference would be negative 7, and then we multiply it by n. Now we're to where we were in that last problem, where we don't know this value here. And I explained this in the lesson video for 8.2. This value is kind of like a 0 term of an arithmetic sequence. This is the first term, 9, so if there were a term in front of that, we could call it the 0 term. So following the same pattern, if we had to subtract 7, what would that 0 term end up being that we would have to subtract 7 from in order to get to 9 for our first term?
16.
And it would have to be 16. So that 0 term would be 16, which means that this value here is 16. And that's our nth term. Also called the explicit formula. What's that?
Or you can use the formula as well, right?
Yeah, the formula in the book is a sub n is first term plus n minus 1 times d. You also, yeah, absolutely, you can use that one. The only reason I jump straight to this is the form that the answer needs to be in eventually. And you'll get there using this formula. Matter of fact, let me show you. So you'd put a 9 right here, and then you'd have n minus 1 multiplied by the common difference, negative 7. If you distribute the negative 7, you get 9 plus negative 7n plus 7, and then you end up with negative 7n plus 16. So you get to the same result, just a couple of extra steps. It's not a big deal. So yeah, you're welcome to use that formula as well. Okay. The other part of 8.2 was what's called a partial sum of an arithmetic sequence. This notation was actually introduced in 8.1. It's called sigma notation. This symbol right here is a Greek letter in the alphabet. It's kind of like a capital letter S. It just stands for summation, meaning we're adding terms of a sequence. We're adding, starting with the first term and ending with the 30th term. So we're adding 30 terms of an arithmetic sequence together, and those terms are determined by this explicit formula. So if you had to in a pinch, if you can't recall the formula for adding a partial sum of an arithmetic sequence, you could just write out all 30 terms of this sequence and try to add them together with a calculator. What I mean by that is if you plug in a 1 for n, you get negative 2 plus 5, so the first term is 3. Now if you plug in a 2, you get negative 2 times 2, which is negative 4, plus 5, which is 1. And it looks like we're just subtracting 2 every time. So you could write out all 30 terms and then add them together like this, and that would be the sum. It takes a long time to do it that way, so there is a formula for the partial sum of an arithmetic sequence. And it's sum of a certain number of terms is equal to the number of terms you're adding, and then the first term plus the last term divided by 2. So what we need to figure out in order to use this formula is how many terms are we adding, and that's 30. We're adding 30 terms for this one. And then what's the first term, and what's the 30th term? And we can find those just by using the explicit formula or the nth term there. But if I plug in a 1 like we did, we get negative 2 plus 5, which is 3. So the first term is 3. If I plug in a 30 for n, I get negative 2 times 30, that's negative 60. So if you add 5, you get negative 55. So if you plug all that into the formula, you're going to have 30 and then 3 plus negative 55 all over 2. So that's 15 times negative 52 and that's negative 780. So the sum of the first 30 terms of that sequence is negative 780. And by the way, there will be a formula sheet on the test that gives all the formulas in Chapter 8. It just doesn't name them. So you'll see this formula on the formula sheet, for example. It won't be titled as the partial sum of an arithmetic sequence. It's up to the student to know which formula is which, but you'll have the partial sum formula, you'll have the nth term of a arithmetic sequence there. You'll have all the formulas, you just have to know which one is which. Does that make sense?
Yep.
Okay. So now we're moving on to, these questions are all from 8.3. That one's 8.3. This one's 8.3. We have 8.3. That one's also, so this whole page is 8.3. So 8.3, we were introduced to a geometric sequence. Geometric means instead of adding or subtracting the same term over and over again, you're multiplying by the same term over and over again. So let's see. Determine if the sequence could be geometric. Well, all that means is, are you multiplying by the same number to go from term to term? So let's see, 2 to negative 10, and then negative 10 to 5, what is that, 50, and then negative 50 to 250. Looks to me like we're multiplying by negative 5 every time. So if that's the case, it is geometric. And instead of calling it a common difference like with arithmetic sequences, we call this a common ratio. So R equals negative 5. Now with some geometric sequences, it's a little harder just to look at the terms and then determine if there's a common ratio. So one way you could determine this is just take one term and divide by the term in front of it. So negative 10 divided by 2 is negative 5. And then just take the next term and divide it by the term in front of that. 50 divided by negative 10 is negative 5. And keep going up and make sure you keep getting the same value every time. Negative 250 divided by 50 is negative 5. And that's all question 6 is asking, is it geometric? If it is, find the common oh, and then this one. The nth term, yeah, I didn't see that. Okay, nth term, geometric is relatable to exponential. So y equals a times b to the x minus 1. This is how we're gonna use an exponential in form for geometric sequences. And this value a is just the first term, and the value b is the common ratio. So exponential or geometric sequences is always first term multiplied by the common ratio raised to a power of n minus 1. So for this problem, it's going to be 2 as our first term, and then negative 5 as our common ratio raised to a power of n minus 1. That's how nth terms of geometric sequences are formed. So those ones are pretty easy to form, at least the nth term. Any questions on that one?
So we'll just finish, right? Like 2 times minus 5.
Yeah, you just leave it like that. Yep. And like I said in the last page, it's never a bad idea just to double check once you have an nth term. Just make sure that this formula generates this sequence right here. So for example, if I wanted to plug in n equals 1, then 1 subtract 1 is 0, negative 5 to the 0 power is 1, and then 1 times 2 is 2. So it gives me 2 like it should. And then you can check it for even the second term. If you plug in a 2 there, 2 minus 1 is 1, negative 5 to the first power is negative 5, and then negative 5 times 2 is negative 10. So it looks like it's given us the values that we need in that sequence. Okay, 7 is asking us to find... Let's see, find the fifth term of the geometric sequence. So we know the third term. The third term is 63 fourths. We don't know the fourth term. We don't know the fifth term. The sixth term is... And key word here is this geometric. So what we need to figure out is, if it is geometric, what's the common ratio? So what is r? R equals what? And they haven't told us that. And the reason I've written it out like this is, knowing that it's geometric, I know that I'm going to multiply by a certain value r, the common ratio, to go to this term. And then I'm going to multiply by that same value r to go to this term. And then I'm going to multiply by r again to go to that term. So what we've just created is an equation, 63 fourths multiplied by r cubed equals 1,701 over 32. In order to go from the third term here, where n equals 3, to the sixth term when n equals 6, I had to multiply by r 3 times. So that's r cubed. And if we solve this equation here, we could figure out what that common ratio is. And then we could either generate an nth term, or we could just multiply by that common ratio to get to the fifth term. So now, how do we solve this? How do we solve this equation? We need to get r cubed by itself and then cube root. So I would suggest we get rid of that fraction by multiplying by a reciprocal on both sides. So then we have r cubed let's see, 4 over 63. And then 27/8. So r cubed equals 27/8. When I multiplied these two together, I got 27/8. in a cube root both sides now. Then we get r equals cube root of 27, which is 3, and the cube root of 8, which is 2. So the common ratio that multiplies each term is 3/2. So we could proceed one of two ways, and what I'm going to suggest now may seem like a little more work initially, but it might prepare everyone better for the exam. I know it says find the fifth term specifically, and it doesn't ask for the general term, the nth term, but it's not a bad idea to try to find the nth term. Reason being is if I had given you the third term and the sixth term and then asked for the 40th term, you're not going to want to multiply by 2/3 40 times to try to get up to that 40th term. You're going to want to have an nth term expression that you can just plug n equals 40 into to find that 40th term. So I'm going to go ahead and find an nth term. This right here. We know the common ratio. We know the common ratio is, what was it? 3/2. So I can plug in a 3/2 for r. I don't know the first term, but I do know that the third term, for example, if I plug in a 3 for n, then I could plug in for a sub n, I could plug in 63/4. So then if we have 63/4 equals a sub 1, let's see, 3 minus 1 is 2, 3/2 squared is 9/4. We can multiply by 4 9s. And the 4's cancel. 63 divided by 9 gives us a first term of 7. And this is getting really messy. I'm writing stuff all over the place. But going back to our nth term up here, we can say now that our nth term is 7 times 2/3 to the n minus 1. And the point of generating that nth term is now I can find any term that's asked, whether it be the fifth term or the 50th term. In this case, they asked about the the fifth term. So using that nth term, I can just plug in a 5 and say that the fifth term, a sub 5, is 7 times 2/3 to the 5 minus 1, which is 4. 2 to the 4th power is 16, 3 to the 4th power is 81, so it's 7 times 16/81. Which is 112/81. So the fifth term, I know it's a long explanation for a problem, but the fifth term is 112/81. Any questions on that one? The other way, if you didn't want to come up with the nth term, the other way could have been, well, you know the third term, so just multiply by 2/3 to get the fourth term, and then once you know the fourth term, multiply by 2/3 again, and then you can get the fifth term. But I think it's helpful to have that nth term because, you know, I could have asked about the 10th term or the 20th or the 30th, and you wouldn't want to have to multiply by 2/3 every time to get up there. All right, question 8. This symbol, again, means sigma notation. That means summation. And it's a partial sum because you're only adding 5. But it's not a partial sum of an arithmetic sequence like we did on the last page. This is called a partial sum of a geometric sequence. And that has a different formula. The sum of a certain number of terms of a geometric sequence is first term times 1 minus r to the n divided by 1 minus r. And again, you don't need to memorize this formula per se. You just need to be able to recognize it when you see it and know that this is the formula for a geometric sequence partial sum. So what we need to know then is what's the first term and what's the common ratio. And we can use this to generate the first term. If I plug in a 1 for k right here, I get negative 2/3 to the first power, which is negative 2/3. So I know the first term is negative 2/3. And then the base of this expression, the exponential expression, is negative 2/3. And the base of an exponential, if it's geometric sequence, is also your common ratio. So that is also our common ratio. So all we need to do is plug this into the formula now. The sum of the first term times 1 minus the common ratio raised to the power of n. In this case it's 5 because we're adding 5 terms. And then 1 minus common ratio. So this wouldn't be something I would recommend doing by hand. This part, at least, trying to figure out what this is definitely work that you would do on a calculator. And I wouldn't even plug this whole thing in at once and try to hit enter. I'd plug it in pieces. I would start with the fraction here, negative 2/3 to the 5th power, then subtract that from 1, then multiply it by negative 2/3, and then divide it by whatever that is. Just do it in pieces. So negative 2/3 to the 5th power. Can you guys still see my screen on that thing?
Just to calculate.
Yeah. Let's see, we don't want that. There we go. Negative 2/3 to the 5th power. Then I'm going to 1 minus that answer. And I multiply that answer by negative 2/3. And then I divide that answer by 1 minus negative 2/3, which is 1 plus 2/3, which is 5/3. So that answer divided by 5/3. It's negative 0.452. Let's see if that can be turned into a fraction. So we're going to keep it negative 0.453.
Wait, so how with the ratio?
Say again.
How do you come up with the ratio again?
The common ratio r.
Ratio, yeah.
So you can do it a couple of ways. Because the expression given, and it said it's geometric, it's exponential in form, negative 2/3 raised to the power of k. Anytime you have a variable in the exponent, it's exponential. So the base of that exponential is always going to be your common ratio. Another thing you could do, we found the first term was negative 2/3. If I had found the second term, I would just plug in a 2 right here for k. And then I get negative 2/3 squared, which is 4/9. And then if I wanted to get the third term, it'd be negative 2/3 raised to the 3rd power. So that would be negative 8/27. So these are just the first 3 terms of the sequence. And like I was explaining, I think in question 6, sometimes it's hard to look at a sequence like this and figure out what the common ratio is, but one thing you could do is just take one term and divide it by the term in front of it. So if you had 4/9 divided by negative 2/3, you get negative 2/3. If you did the same thing with this and took it and divided it by the term in front of it, negative 8/27 divided by 4/9 is negative 2/3. So the common ratio ends up being negative 2/3. Does that answer your question?
Yeah. So first term in that problem?
No, this one's a little tricky. So it's not on the practice exam, but if we had another one to look at, like let's do the sum from I equals 1 to 7 of negative 2 times 3 to the I minus 1. So now the base of the exponential is 3. So the common ratio would be 3. And then the first term you find by letting I equal 1. So if I plug in a 1 right here for I get 1 subtract 1, which is 0. 3 to the 0 power is 1, and then 1 times negative 2 is negative 2. So the first term would be negative 2. Is that what you were asking?
Yes, yeah.
Okay. Does that answer your question?
Yeah, it does.
Okay. All right. So that's called a partial sum because we're only adding 5 terms of the sequence. The difference in question 9 is we're adding an infinite number of terms, and that's only possible on a geometric series. A series means a sequence where you're adding the term together. That's the difference in vocabulary there. But the infinite sum of a geometric series is only possible if the absolute value R is less than 1. The geometric series will only have an infinite sum if the absolute value of R is less than 1. So we need to first figure out what the common ratio is of this geometric series. So to go from 2 to negative 2/5, and then to positive 2/25, and then to negative 2 1/25, what is it that we're multiplying by every single time?
Negative 1/5.
Yeah. R equals negative 1/5. And if we took the absolute value of that, we'd get 1/5, and 1/5 is less than 1. So this geometric series does have an infinite sum. And it's always a good idea to check. Just because it asks you to find an infinite sum, it doesn't always mean that it's possible. If the ratio is bigger than 1, then the answer would just be not possible. If it is possible, you use this formula. The sum of an infinite geometric series is first term divided by 1 minus r. So it's a really simple formula, but it only works if the common ratio is less than 1. So we know the first term is 2, and then 1 minus the common ratio. 1 plus 1/5 is 6/5. And then 2 divided by 6/5 is the same as 2 multiplied by 5/6, which is 10/6, or 5/3. So if this sequence here continued indefinitely and we added every single term all the way out to infinity, the sum of that series approaches 5/3 is the way that we think about this. And I know it can be hard to wrap your head around adding an infinite number of terms, but I tried to give a pretty good and detailed explanation on that video for 8.3 that you can watch to kind of to see how that's possible to add an infinite number of terms and have it approach a single value. What questions do you guys have on that one? Okay. The answer to this could have been not possible if the common ratio was bigger than 1. So that's something to keep in mind on an infinite geometric series.
So you just write.
Yeah, our textbook doesn't use some of the same vocabulary as others. Other textbooks say the series diverges. If it doesn't approach a particular value, you say it diverges. If it approaches a particular value like this one, you say it converges. So if it doesn't have an infinite sum, you would say it diverges. Or you can just write the sum is not possible. Okay, question 10 was from 8.6. We skipped section 8.4 and 8.5. 8.6 is called expanding a binomial. And honestly, the quickest way to do that is using Pascal's triangle. Pascal's triangle is a triangle made of rows of numbers. The top row is always 1. The second row is 2 ones. The rows always start with a 1, always, and it always ends with a 1. Any term in the middle is found by adding the 2 terms above it. So this term would be 2 because 1 plus 1 is 2. So the next row begins with a 1 and ends with a 1. If you add 2 and 1, you get a 3. If you add this 2 and 1, you get a 3. And if we're raising it to the 5th power, you need 6 rows of Pascal's triangle. You'll always need one more row than the power it's being raised to. So I need this row and then this row. So this is the row of Pascal's triangle I'm going to use for this expansion. Now, the general expansion, I'm not going to use 3x minus 2 yet. I'm just going to change that into a plus b. So the general expansion for any binomial raised to the 5th power is you start with the first term, a, you raise it to whatever power this is, so a to the 5th. Then the next term, oh, and you use this coefficient right here, so it's 1 times that. The next term is going to use this as a coefficient, so it's going to use 5. And then the first term a is going to decrease in power, so it's going to be a to the 4th. And then you're going to use this term to the 1st power. The sum of the powers always has to equal the original exponent there. And now the next term is going to use that as a coefficient, so it's going to be 10. And then the first term decreases to a power of 3. And that second term there increases to a power of 2. And then it's 10a squared b cubed, and then 5a b to the 4th, and then 1 times b to the 5th. This is the pattern that you use for binomial expansion. And the reason you need Pascal's triangle is you need to know what these coefficients are. 1, 5, 10, 10, 5, 1. So once we have that as a general pattern, we can look at the actual binomial we were trying to expand, which is 3x minus 2. Raised to the 5th power. And then continue the expansion using that pattern. Okay, so then instead of a to the 5th, it's going to be 3x. So we're just going to replace all the a's with 3x. And then moving on to the second term, I've got 5 as a coefficient. Instead of a, I can replace that with 3x to the 4th. And then instead of b, that's going to be replaced with negative 2. So that's negative 2 to the 1st power. And then you move on to the next term, which has a coefficient of 10. And then instead of a cubed, it's 3x cubed and then negative 2 squared. And then you move on to this term, so that's going to be 10 and then 3x squared and then negative 2 cubed. And you move on to that term, which is 5 coefficient, and then 3x to the 1st power and then negative 2 to the 4th power. Finally, you have 1 times negative 2 to the 5th power. And then you go through each term and simplify as best you can. So this first term, 3x raised to the 5th power, let's see, 3 to the 5th is 243, so that's going to be 243 x to the fifth. And then for the next term, you got to just be careful and make sure you go slow enough so you don't make mistakes. So you've got -2 to the first power, which is -2. You've also got 3 to the fourth power, which is 81 x to the fourth, and then we have to multiply that by 5, and then we have to multiply that by -2. So -2 times 81 times 5 is -810. So that's actually, I wrote a plus here, but it should be minus because it's -810. So minus 810 x to the fourth. And then you do the same thing for each term, just simplify the exponents and then multiply all the coefficients together. So we've got -2 squared, which is 4, and then 3 cubed there is 27, and then times 10, so 10 times 27 times 4, so that's 270 times 4, it's positive 1080. X cubed. And then with that term, you're going to have a -2 cubed, so that's -8. And then we're going to have a 3 squared there, so that's 9. And then we got a 10 there, so 10 times 9 times -8 is -720. So that's minus 720x squared. And with that term, we're going to have a 16, we're going to have a 3, and a 5. So that's 15 times 16, which is 240. And finally, -2 raised to the fifth power is actually -32, so instead of a plus, I'm going to put a minus 32, and that is the expansion 3x minus 2 raised to the fifth power. That's what it means to expand a binomial. And that was it for 8.6. It was kind of a short lesson, not many homework problems. I think it was only 5, really just to practice this right here. So the reason it said using Pascal's triangle is we needed that row in order to determine what our coefficients were going to be. If it had been raised to the fourth power, then you use the fifth row of Pascal's triangle, which would have been that. That would have given you your coefficients.